H2S boils at minus 60 degrees Celsius. H2C boils at minus 42 degrees. H2T boils at minus 2 degrees. Do you see the trend? As the molecules get heavier, they boil at higher temperatures. That makes perfect sense. Heavier molecules have more electrons. More electrons means stronger London dispersion forces, those weak but universal attractions between all molecules. More stickiness, higher boiling point. Nice, clean, predictable. Now, if you extrapolate this trend upward to the lightest member of the family, the molecule with the fewest electrons and the lowest molecular weight, you'd predict that water should boil at something like minus 70 or minus 80 degrees Celsius, way below zero. Water should be a gas at room temperature. Instead, water boils at plus 100 degrees Celsius. It is not just off the trend, it is off the planet. The gap between the predicted boiling point and the actual boiling point is roughly 170 degrees. That's not a small error. That's a colossal disagreement between theory and reality. If you predicted a building would be 2 stories tall and it turned out to be 50 stories tall, you'd say something is very, very wrong with your prediction. Or something is very, very unusual about that building. And it's not just the group 16 family. You see the same pattern with the hydrides of nitrogen and fluorine. Ammonia, NH3, and hydrogen fluoride, HF, both have abnormally high boiling points compared to their heavier cousins. The pattern is the same. The lightest member of each family has a wildly elevated boiling point. Something special is happening when hydrogen teams up with oxygen, nitrogen, or fluorine. And that something is the hydrogen bond. But I'm getting ahead of myself. We'll come to that. And think about what this means. If water boiled where chemistry says it should, at minus 80 or so, there would be no liquid water on the surface of the Earth. Not at room temperature. Not anywhere except maybe the coldest craters of the polar ice caps. The oceans wouldn't exist. Rain wouldn't exist. Rivers, lakes, clouds, fog, dew, none of it. And you, who are roughly 60% water by mass, certainly wouldn't exist. Something is making water molecules cling to each other with extraordinary, unreasonable tenacity. Something is giving water an absurdly high boiling point for a molecule of its size. Hold that thought. Now let's talk about heat. Suppose you put a pot of water on the stove. You turn the flame on. You wait. And you wait. And you wait some more. It takes a long time to boil water, doesn't it? Much longer than you'd expect. There's a reason for that. Water has a bizarrely high specific heat capacity. What that means in plain language is that water is a glutton for energy. You can pour heat into water, and its temperature goes up only slowly, reluctantly, as if the water is absorbing all that energy and hiding it somewhere. Let me give you a comparison. Take the same mass of iron, put the same amount of heat into the iron. The iron's temperature shoots up almost 10 times faster than the water's. Iron is easy to heat. Copper is even worse. Sand, rock, air, all of them heat up faster than water by large margins. Water absorbs heat energy and just sits there, barely warming up, like a fat cat in the sun that refuses to move. It soaks up energy like a sponge, soaks up water, if you'll forgive the circular metaphor. Now, why does this matter? It matters enormously. It's the reason the ocean moderates the climate of the entire planet. Coastal cities don't get as hot in summer or as cold in winter as cities far inland. The ocean acts as a vast thermal battery, absorbing tremendous quantities of heat in summer without heating up too much, and releasing that heat slowly in winter. Without water's anomalous heat capacity, the temperature swings between day and night, between summer and winter, would be savage. Life on land would be far more difficult, perhaps impossible. And your body uses the same trick. You are, as I said, about 60% water. That water stabilizes your internal temperature. When you exercise, your muscles generate heat. If your body were made of something with a normal specific heat, you'd cook yourself alive every time you ran for a bus. But all that water absorbs the excess heat, keeping your temperature stable. Then you sweat, and the water evaporates, and that carries the heat away. Which brings me to yet another anomaly. Water has an extraordinarily high heat of vaporization. That means it takes a lot of energy to turn liquid water into steam, much more than you'd expect for a molecule of its size. When sweat evaporates from your skin, each gram of water that escapes carries away about 540 calories of heat. That's a lot. That's why sweating cools you so effectively. If water had a normal heat of vaporization, sweating would be almost useless as a cooling mechanism. Let me keep going. Water has the highest surface tension of any common liquid except mercury. Surface tension is what makes water form droplets instead of spreading into a thin film. It's what lets you carefully place a steel sewing needle on the surface of water and watch it float, even though steel is almost 8 times denser than water. The surface of the water acts like a stretched membrane, an elastic skin, and something is pulling those surface molecules together with unusual force. The same surface tension drives capillary action. If you dip a thin glass tube into water, the water climbs up the tube against gravity. The narrower the tube, the higher it climbs. This seems like magic. Water is going uphill with no pump, no energy input that you can see. How? The water molecules at the edge of the tube are attracted to the glass. They form hydrogen bonds with the silicon and oxygen atoms in the glass surface. So the water at the edge creeps upward, wetting the glass. But as that edge water rises, it pulls on the water behind it through the network of hydrogen bonds within the liquid. Surface tension holds the column together. The result is a column of water that climbs the tube until the weight of the column exactly balances the upward pull of adhesion and surface tension. This is how trees work. Let that sink in. A giant redwood, 300 feet tall, pulls water from its roots to its topmost needles entirely by capillary action and transpiration. There are no pumps, no hearts, no mechanical devices, just tiny channels in the wood, capillaries, and the relentless pull of water's surface tension and hydrogen bond cohesion. Water clings to the walls of those channels, and the evaporation of water from the leaves at the top creates a suction that pulls the whole column upward. If water had a normal surface tension, this wouldn't work. Trees couldn't exist above about 5 or 10 feet. There would be no forests, no jungles, no ecosystems built around large plants. The land surface of the earth would look completely different, and the species that depend on forests, which is most species, would never have evolved. Water is also an exceptional solvent. More substances dissolve in water than in almost any other common liquid. This is why water is sometimes called the universal solvent, although that's a slight exaggeration. The reason is, again, water's polarity. Those slightly positive and slightly negative ends of the water molecule can surround and pull apart ionic compounds like table salt and can form hydrogen bonds with many other molecules, keeping them in solution. The biochemistry inside your cells depends absolutely on water's ability to dissolve and transport an enormous variety of molecules. So let me take stock. Here is the charge sheet against water. It expands when it freezes. It boils at an absurdly high temperature. It has a freakishly high specific heat. It has a freakishly high heat of vaporization. It has a freakishly high surface tension. It's an abnormally good solvent. And every single one of these anomalies is essential for life on Earth. Now, here is the question that any self-respecting physicist must ask. Is there one explanation for all of this, or do we need 6 different explanations? This is the beautiful part. There is one explanation, one single underlying mechanism that accounts for every one of these strange behaviors, and it's called the hydrogen bond. Let me build this up carefully, because it deserves to be understood properly. A water molecule is shaped like a boomerang. The oxygen atom sits at the bend, and the 2 hydrogen atoms stick out at an angle of about 104.5 degrees. It's not a straight line. It's bent, and that bend is critical. Now, oxygen is a very greedy atom when it comes to electrons. Chemists call it highly electronegative. Among the common elements, only fluorine is more electronegative. What this means is that oxygen pulls the shared electrons in the OH bonds toward itself. It hogs the electron cloud. This leaves the hydrogen ends of the molecule slightly electron poor, slightly positive. And it leaves the oxygen end electron rich, slightly negative. The water molecule is what we call a polar molecule. it has a plus side and a minus side, like a tiny bar magnet. When you have a bunch of these polar molecules near each other, the positive hydrogen on one molecule feels an attraction to the negative oxygen on a neighboring molecule. This attraction is what we call a hydrogen bond. Now wait, I need to be careful here, because the name is misleading. A hydrogen bond is not a regular chemical bond. The covalent bond that holds the atoms together inside a single water molecule, the OH bond, is strong. It takes a lot of energy to break. A hydrogen bond is maybe 1/20th as strong as a covalent bond. It's relatively weak, but, and this is the crucial distinction, it is much, much stronger than the ordinary van der Waals forces, the London dispersion forces, that hold most other liquids together. A hydrogen bond is in a middle category. Not as strong as a real bond, but 10 or 20 times stronger than the flimsy forces that hold together a liquid like, say, hydrogen sulfide. And here's the thing that makes water special. Each water molecule can form not one, not two, but up to 4 hydrogen bonds simultaneously. 2 through its 2 hydrogen atoms acting as donors. 2 through the 2 lone pairs of electrons on the oxygen, acting as acceptors. 4 bonds per molecule. 4 sticky hands reaching out and grabbing 4 neighbors. And those neighbors are doing the same thing. Each of them grabs 4 others. And those grab 4 more. The result is a 3-dimensional network of hydrogen bonds threading through the entire liquid. Every molecule is connected to its neighbors, and those neighbors are connected to their neighbors, forming a vast, constantly shifting, flickering web of connections. In most liquids, the molecules are held together by weak forces and they slosh around almost independently. In water,